Welcome to Deep Dive.
Great to be here.
So today we're jumping into something really fascinating based on some insights from a video we looked at.
Yeah, it's all about failure engineering, right? And these unexpected events.
Exactly. Black Swans, they call them sometimes.
Mm-hmm.
How even really well thought out plans can just completely unravel.
Uh-huh.
We're going to start with Chernobyl as, well, a prime example.
A huge one. The video really laid out how it became the biggest nuclear catastrophe in history, April '86.
And the fallout, I mean, the numbers were staggering. 400 times Hiroshima, apparently.
And the craziest part, it all kicked off with a safety test.
Right. A test to see if the turbines could power things briefly during an outage, until the backup generators started. Seems sensible on the surface.
Deceptively so.
So maybe we should quickly recap how these reactors generally work. Just the basics.
Sure. So you got neutrons splitting uranium atoms. That's fission.
Creates a chain reaction.
Exactly. A chain reaction releasing a huge amount of heat.
And that heat boils water.
Right. Makes steam, drives turbines, generates electricity. Pretty standard process for nuclear power.
Okay. And the key to not having it run away is control rods.
Precisely. They absorb neutrons, kind of like brakes on the chain reaction. You raise them to speed things up, lower them to slow down.
Got it. So during this test at Chernobyl, what went wrong?
Well, a few things went wrong critically. First, the power level dropped way, way too low, down to like 200 megawatts.
And it was supposed to be much higher?
Yeah, the instructions said keep it above 700 megawatts minimum. This huge drop caused a buildup of fission byproducts, particularly something called xenon gas.
And xenon, that's bad news in a reactor.
At this point, yes. It acts like a sponge for neutrons, soaking them up even more.
So the low power causes xenon buildup, and the xenon makes the power go even lower.
Exactly. A nasty feedback loop. They were trying to break, but it just made things slower and harder to control.
Okay, that sounds problematic enough.
But then you add in the specific design of that reactor, the Soviet RBMK. It had this thing called a positive void coefficient, but crucially, at low power.
Positive void coefficient. What does that mean, basically?
It means that when water turns into steam creating voids or empty spaces, it actually speeds up the nuclear reaction instead of slowing it down.
Wait, steam makes it go faster? That seems counterintuitive.
It is. In most reactors, it's the opposite, a negative coefficient, which is much safer. But in the RBMK, at low power, more steam meant less water to moderate neutrons and, paradoxically, a faster reaction.
So the operators are struggling with low power because of the xenon.
Right. So they try to fix it. They start pulling out more control rods to increase the reaction rate.
Which, combined with this positive void coefficient,
was catastrophic. As power started to rise slightly, it created more steam voids. Those voids made the reaction go even faster, which made more steam.
Another feedback loop.
Yeah.
But this one's speeding things up uncontrollably.
Exactly. A runaway reactor. Power surged incredibly rapidly.
And that led to the explosion.
2 explosions, actually. Steam explosion first, then a second one possibly involving hydrogen, blew the reactor apart.
The video mentioned experts weighing in afterwards, like Hans Bethe.
Yeah, Nobel laureate Hans Bethe had basically said the RBMK design itself was fundamentally flawed, just asking for trouble, ill-prepared for human mistakes.
And the Soviet scientist, Legasov.
Valery Legasov, right. He acknowledged the design flaws too, but also pointed to what he called the stupid decisions by the operators going against safety rules.
So it's a mix. Bad design and human error.
It seems like a combination. The video kind of presented both. The systemic issues maybe within the Soviet system, lack of transparency perhaps, plus a reactor design with known issues, plus operators making critical mistakes under pressure.
It really shows how hard it is to engineer out the human factor completely, and how weird sequences of events can just align perfectly for disaster.
Absolutely. And that difficulty in predicting failure, especially human-driven failure, ties into the next part the video explored. It shifted gears a bit.
Right, to finance. With long-term capital management, LTCM.
Exactly. A hedge fund run by, incredibly smart people, including 2 Nobel Prize winners in economics.
You'd think if anyone could manage risk, it'd be them.
That was the assumption. They had these complex models, tons of data, and they were incredibly successful for a while.
But
Then, boom, within about 4 months, they collapsed. Went from billions in assets to, 100 billion in debt.
100 billion, wow.
Yeah, the New York Fed had to step in and organize a massive bailout to prevent wider financial chaos.
So even geniuses with Nobel Prizes couldn't foresee this catastrophic failure.
Which perfectly illustrates the idea of Black Swans, right? That concept Nassim Nicholas Taleb popularized, which the video brought up.
These are the totally unexpected game-changing events.
Yeah, rare, massive impact, impossible to predict beforehand, but everyone goes, oh, of course. In hindsight, LTCM was a classic financial black swan.
And the video explained why standard statistics often miss these.
Right, because traditional models often rely on past data and assume things follow a nice, predictable pattern, like a bell curve, the normal distribution.
But real life, especially human systems, isn't always that neat.
Not at all. The video used a great example. Human weight versus human wealth.
Okay.
If you take the average weight of 1,000 people, adding one extremely heavy person doesn't change the average that much. Things are sort of clustered around the middle. Bell curve works okay.
Right.
But take the average wealth of 1,000 people and then add someone like, Elon Musk or Jeff Bezos.
It completely skews the average.
Totally. Because wealth and many other things like book sales, city sizes, follows a different pattern, often called a power law. It has fat tails, meaning extreme outliers are much more common and impactful than in a normal distribution.
So using bell curve thinking for stuff that follows a power law
means you drastically underestimate the possibility and impact of extreme events. You basically assume black swans can't happen or are so rare they don't matter, which, as LTCM showed, can be disastrous.
Okay, so if prediction is so hard, especially for these black swans, what's the alternative? The video moved on to fail-safe design then, right?
Exactly. Fail-safe. The philosophy here isn't about predicting every possible failure.
It's about designing the system so that when it fails into a safe state by default.
Precisely. Think of the train brakes example they gave.
The air pressure ones.
Yeah. The system needs air pressure to keep the brakes off. If the pressure is lost for any reason, a leak, a failure, the brakes automatically engage.
So failure mode, safe mode. Stop the train.
Right. It doesn't try to have 5 backup air pumps. It just makes the default state safe. The video even had that funny bit comparing it to a Whale Jessar song lyric.
About making a breakup the most beautiful breakup. Like planning for the failure itself.
Kind of anticipate mindset.
The fail-safe isn't foolproof either, is it?
Yeah.
The video brought up the Boeing 737 MAX crashes.
A very tragic counterexample, the MCS system maneuvering characteristics augmentation system.
That was intended as a safety feature, right? To prevent stalls.
Yes, it was meant to automatically push the plane's nose down in certain situations to mimic the feel of previous 737 models and prevent a dangerous high angle of attack.
But the problem was,
it relied on a single sensor, an angle of attack sensor. And if that sensor gave a faulty reading,
the system thought the plane was stalling when it wasn't.
Correct, and it would activate, pushing the nose down. Critically, it could reactivate repeatedly, and pilots weren't initially well-trained on how to counteract it effectively. It could override their inputs.
Creating this terrifying loop where the pilots are fighting the plane's own safety system.
Exactly. A failure in the fail-safe concept's implementation, relying on a single point of failure, complex automation, and maybe insufficient pilot training on the new system, it led to catastrophe.
Which then brings us back to nuclear power, but this time Fukushima in 2011.
Right. And Fukushima is interesting because, unlike Chernobyl's RBMK, the reactors there did have fail-safe features, like that negative void coefficient we mentioned earlier.
Meaning steam should slow the reaction, not speed it up.
Correct.
Oh,
inherently more stable. And when the massive earthquake hit,
the reactors shut down automatically.
They did. The primary safety systems worked as designed. The chain reactions stopped.
But that wasn't the end of the story.
No, because even after shutdown, the fuel rods are still incredibly hot from residual decay heat. They need constant cooling for a long time.
And that cooling requires power.
Power for the pumps. They had backup diesel generators for exactly this scenario.
But then came the tsunami.
Triggered by the earthquake, yes.
Oh.
And it wasn't just any tsunami. It was enormous, far larger than the plant's seawalls were designed to withstand based on their risk assessments.
Another Black Swan event. Basically, this unprecedented combination of quake and tsunami size.
That's how the video framed it. The tsunami flooded the site and, crucially, knocked out the backup generators.
So no power for cooling.
No power, no cooling. Despite the reactors being shut down, the cores overheated, leading to hydrogen explosions and meltdowns.
Wow. So even with a safer reactor design and shutdown systems working, this external Black Swan event overwhelmed everything.
It did. And the video highlighted an intriguing detail comparing Fukushima Daiichi with the Onagawa plant nearby.
Onagawa was closer to the epicenter, wasn't it? But it survived largely intact.
That's right. And one key difference investigators found was in their tsunami preparedness. Onagawa's engineers had apparently considered historical tsunami data going back maybe 1,000 years?
1,000 years.
Whereas Fukushima Daiichi's planning was based more on, say, the last 100 years or so of data.
Which didn't include an event of this magnitude hitting that specific spot.
Exactly. So Onagawa built higher sea walls based on that deeper historical look, and those walls held. It shows the danger of relying only on recent data for predicting really extreme natural events.
So Fukushima wasn't necessarily about a flawed reactor design like Chernobyl, but about being overwhelmed by an event that exceeded their planning parameters.
Largely, yes. Though investigations also pointed to issues like maybe overconfidence from the plant's management, a belief that such a massive disaster just wasn't possible there.
Which might have led to less robust preparations or slower responses?
Potentially. So even without the same kind of systemic issues maybe seen at Chernobyl, Fukushima still ended up as a level 7 nuclear accident, the highest level, same as Chernobyl.
It really underscores the immense challenge of managing these incredibly complex, high-risk technologies.
Absolutely. Our brains aren't really wired to intuitively grasp these super low probability, high consequence events. Science has limits. The world keeps getting more complex. It makes us vulnerable.
So what's the final takeaway then? Are we just doomed to be hit by black swans?
Well, the video didn't suggest doom exactly, more like realism. We have to accept that absolute safety, perfect prediction, it's probably impossible in these complex systems.
We learn from failures. We implement things like fail-safe designs, which do help.
Yes, definitely. We improve. But we also need to acknowledge the limits of our knowledge and prediction.
And maybe focus more on resilience, being able to cope with the unexpected when it does happen.
I think that's a big part of it. Humility about what we don't know, vigilance, and adaptability. Accepting that unforeseen high-impact events are just part of the landscape.
It's a powerful reminder, certainly, even with all our technology and best intentions.
Indeed.
Well, that's all we have time for on this deep dive. Lots to chew on there.
Definitely makes it think.
Thank you for joining us. We hope this gave you some perspective on these complex ideas of failure, prediction, and just how unpredictable things can sometimes be. Until next time.